Thank you. So today my topic is hydrodynamic performance of a biomimetic robotic dolphin actuated by IPMC. First, I introduce this material developed in our lab. It is called IPMC, and it is a smart material. It has a sandwich structure with polymer inside and electrodes chemically plated on both surfaces. When we apply a voltage across signal direction, it will bend. So based on these characteristics, we can use it for underwater actuating. So the first goal of our project is for engineering. So we develop a small robotic fish with IPMC as actuators. So the robotic fish can be used in various areas, such as underwater exploration or microchannel detection. Since the fish is very small, so it's about 20 millimeter long, so the power it carried is limited. So it's important to know the thrust performance. And the second goal of my project is about biological. Since we know fish at different scales, they have different swimming modes, like eels, small fish, they have different swimming wavelengths compared to big fish, like tunas. So we're going to use this robotic to help us to understand the thrust performance of robotic fish at different scales. And by changing the viscosity of the fluids, we can change the Reynolds number. And in that case, we can change the scale. And first, we develop a theoretical model, and this is simulation results since it doesn't come out. And we also conducted a series of experiments to test the robotic fish, and this is our results. Based on our image analysis, we capture the motion of the IPMC, and we get the wavelength of the robotic fish. And the wavelength is a very important parameter to distinguish the different fish swimming modes. And then we get the velocity, thrust, and power. Then finally we get the thrust efficiency. And by comparing the results of theoretical results and the experimental results, both results match pretty well. And we get, based on the results, we also get two conclusions. First conclusion is that the thrust efficiency of the robotic fish varies from 50% to 8% at different scales, which is relatively close to that of real fish. And the second conclusion we get is we notice that the optimal frequency varies for fish at different scales to get the maximum thrust efficiency. And combining with the wavelength results, and we can conclude that fish at different scales have different swim modes to get the maximum thrust efficiency. And this result has a good agreement with the results of biologists on real fish. And I think that this work has been published on smart material and structures. And that's all my work, and thank you. And good luck to the rest slammers.